Qubits are the most fragile things in computing. One stray photon and your calculation is gone. So quantum error correction, the hardest engineering problem in computing, explained. Here's the problem. Qubits lose their quantum state constantly. Heat, electromagnetic radiation, vibrations, even neighboring qubits interfere. This is called decoherence. The quantum information leaks into the environment. Typical coherence time, microseconds to milliseconds. That's how long you have before. Every quantum error boils down to three types. Bit flip, the X error 0 becomes 1. Phase flip, the Z error, the quantum phase gets inverted. And Y, both at once. Any error, no matter how complex, can be decomposed into combinations of these three Pauli operations. But here's the catch. You can't look at a qubit to check for errors without destroying the. In classical computing, error correction is simple. Copy a bit 3 times. If one flips, majority vote wins. Easy. But quantum, the no-cloning theorem says you cannot copy a qubit. So we need a completely different approach. The solution? Don't copy the state. Enter surface codes, the leading approach. Imagine a grid. Data qubits store your information, ancilla qubits sit between them. The ancillas measure parity, they check if neighboring data qubits agree, without ever looking at the actual values. If a bit flips, the parity changes, and we know where the error is without knowing what the data is. It's like hearing an alarm without opening. This brings us to logical qubits versus physical qubits. Many noisy physical qubits work together to protect one perfect logical qubit. Current estimates, about 1,000 physical qubits per logical qubit. The logical qubit can have an error rate 1,000,000 times lower than any individual physical qubit. That's the goal. Here's the challenge. To run Shor's algorithm on RSA 2048, you'd need about 4,000 logical qubits. At 1,000 physical per logical, that's 4 million physical qubits. Today's best machines have about 1,000. We need 1,000x improvement in scale. That's why fault-tolerant quantum computing is still years away, but progress is accelerating. In 2023, Google demonstrated error rates going down as they added more qubits, crossing the threshold. Microsoft announced topological qubits that are inherently more stable. IBM's roadmap targets over 100,000 qubits. We're at the inflection point, the hardest engineering problem of our recap. Qubits decohere in microseconds. Errors are bit flips, phase flips, or both. You can't copy qubits, so encode redundantly with entanglement. Surface codes use ancilla qubits to detect errors without measuring data. Cost, about 1,000 physical qubits per logical qubit. Hope, if error correction fascinates you, subscribe for more quantum deep dives. Next video, quantum supremacy. Has anyone actually beaten classical computers? Comment below.